we'll wrap up this chapter with some vision problems. Not all of these are diseases. In fact, some of these are just the way you're born. You just have eyes that are not really how they should be, but it's not a disease. It's just sort of how your eyeball is shaped. And that's these first two. The first one is nearsightedness or myopia. Listen, you need to know, what is nearsightedness? What is the effect of it? What causes it? And how do we fix it? You also need to know that it's also called myopia. I don't have a good way to help you remember myopia for nearsightedness, but farsightedness is hyperopia. So maybe that helps, like far and hyper. I sort of think of those as being two words that are similar. Nearsightedness or myopia, the image forms in front of the retina. So that is what nearsightedness is. That's the effect of nearsightedness. And it's caused because the eyeball is just too long. Normal, healthy eyeball is not a matter of health. The eyeball is just fine. It's just it's not really shaped correctly. In a normal eyeball, that's where the focal length is for an object that's an infinite distance away. But for a person with nearsightedness or myopia, I'm going to exaggerate this a little bit, but in this one, the light rays come in and then they focus. Their focal point is right there. And so on the retina, where I should be seeing an image, I'm not seeing an image because that's not where the rays cross. Nearsighted people typically can't see far away things. My wife is nearsighted, and she can see things up close just fine, but without her glasses, she cannot see everything. Like if she was looking at a class of students, they would just sort of look like fuzzy blobs to her. Their far point. Remember how we said the far point is usually what? The far point for most people is infinity, that you can just see far things really well. But their far point can be as short as 20 to 40 centimeters. Can you imagine not being able to see anything beyond 20 to 40 centimeters, or everything just sort of being fuzzy? Well, some of you might be nearsighted. You use a diverging lens to correct this. Who can tell me what a diverging lens is? We also called it a concave lens. I always think of it, oh, this lens is caving in. The virtual image created by the diverging lens appears closer. So what the diverging lens, you can think of it in a couple of different ways. Diverging lens create images that are closer than they actually are. Okay, so the image just makes it appear that the image is closer. You can also think of it in this way, and here's a diagram of an eye that has myopia, and then an eye that's corrected so that the myopic eye can now see just fine. These light rays coming in, because it's a diverging lens, they diverge a little bit, and then that allows them to be converged by the convex lens of the eye so that it focuses at the back of the retina. So you can use the lens equation to find the strength of the lens for a particular person. And remember, the strength of the lens, P, is equal to 1 over the focal length. I think we've had this before, but I don't remember. And the power is in units of diopters. If you ever go to the eye doctor, if you've ever had glasses, you know about the strength of the lens. And the strength of the lens describes how much does the lens bend light. Let me pause here for just a second. Okay, so let's imagine that I'm looking at an object that I have a myopic eye, and let's imagine that I'm looking at an object that is an infinite distance away. I say infinite doesn't really necessarily mean it's infinite. Like as I look out, I look onto my neighbor's house. My neighbor's house, as I'm looking at right now, you can imagine I'm looking out my window. My neighbor's house is about, I don't know, 100 feet away. But my eyeball is only a centimeter or two in diameter. And so 100 feet away versus 2 centimeters, that's basically an infinite distance away. It's much, much larger than the diameter of my eyeball. So when I say an infinite distance away, I don't mean like to the edge of the universe. What I mean is just an object that's much farther away than the diameter of my eyeball. So let's say that our object distance, DO, is infinite, but my person has a far point of just 30 centimeters. So if I have a far point of 30 centimeters, then that means that my object I want to be at, or my, sorry, a second. So let's try drawing an image of this. So here's my concave lens. Here's my object, which is like an infinite distance away. And what I want to do is I want to move an image of this object up to about 30 centimeters. So I want to have the image created by this lens to be 30 centimeters. Now, this is going to be a negative value, and that's because this is a virtual image. We're not really getting into that, so don't really worry about that right now. So if I use the lens equation, 1 over f equals 1 over do plus 1 over di, my 1 over do, that's 1 over infinity. That's equal to 0. 1 over a big number is equal to 0. 1 over di, that's going to be my new image distance, and then that's going to equal to f. So f is equal to minus 30 centimeters. Okay, so the focal length would be minus 30 centimeters. And this image that's created by the concave lens is virtual. So the image distance is negative. I'm not going to have you do this on the exam, but it is important for you to understand that these concave lenses, when you're correcting for myopic vision, that's what they're doing, is that they're taking an object that's a really long distance away, and they're really just moving the image up closer to your eye. So it's as if you see that object at a close distance, or the image of that object at a close distance, and then your eye is able to process it. Or you can also think about it in this way, that the lens is diverging the rays and then allowing them to converge at the proper point on the back of the eyeball, on the retina. You can identify a nearsighted person or myopic person by examining their glasses. They are concave or diverging, that are fatter on the outside or thicker on the edge than they are in the middle. Also, the person's eyes should appear smaller. Smaller through the diverging lens. Diverging lenses will make images that are smaller. So we'll take a look. Actually, these days you can't really tell from the lenses because our optometrists have just gotten, our chemists actually, that make these materials, they've gotten a lot better at making materials to make lenses out of, so they're not as thick as they once were. But used to, you could look at a pair of glasses and see the glass literally just sort of poking out from the side of the frame. And then you can also look at their eyes. Take a look. If you know somebody that's really nearsighted, have them put on their glasses and then have them take them off again. The shape of their eyes or the size of their eyes changes. Okay, so farsighted people are hyperopia, farsightedness. Or hyperopia. You do need to know both terms. In these, images form behind the retina. Usually that means that the eyeball is too short. I have a diagram here. So this is a normal, oh no, that's not a normal eyeball. So a normal eyeball would be one where the light rays come in and then they focus there. And remember, for a nearsighted person, the eyeball is too long. Well, for this one, the eyeball is too short. So I have these parallel rays come in, and they focused at a point behind the eyeball. Farsighted people are people that can see far away, so they can't see nearby objects. They cannot see nearby objects. Their near point is farther away, or is farther than normal. The way to do this is you just create or use a convex lens or converging to correct it, and the image of the object appears farther away. So remember, the diverging lens caused the image of the object to appear closer to you. But with a convex lens, it makes the image of the object appear farther away, which is good because farsighted people can't see nearby objects. So they need their object to be farther away. And by using this lens, it causes the object to appear further than it really is, farther away than it really is. And this is like a magnifying glass. Okay, so a couple of age-related problems, presbyopia. Presby is actually the Greek word for elder, like a Presbyterian. Presbyopia is just a form of farsightedness. The near point increases with age. Do you know why that is? Why does the near point increase with age? It's because that lens, it just gets less, it gets more rigid. You can't stretch it out as much. It's not as flexible anymore. As I said, presby is elder, and the person can't see objects that are nearby. The lens loses its elasticity. And just like a farsighted person, you use a converging lens to correct it, or a convex lens to correct this. Oh, I'm sorry, these are reading glasses, but it is a converging or convex lens. You can just pick those up anywhere. You just sort of go try them out. Finally, astigmatism. Here, the lens is not spherical, but oval. Actually, it's a little more complicated than that. The focal points are just different, depending on the axis. This can be corrected with lenses that also have different focal points. Actually, let me just draw you a picture that have different focal points. So in a normal lens, light rays come in from all different points. They all focus up. Now, of course, you have spherical aberration, but that's only from the outer edges, and so we get rid of that with the iris. But typically with a lens, all your focal points, the focal point, you have a single focal point at one point in space. But if you have an astigmatism, you might get light rays that come here and they focus there. Then you have other rays that come into a different part of the lens and they might focus there, or another rays that come in and they focus here. So you just get all these different focal points, and that causes for a fuzzy image. And the way you fix this is that the optometrist will create a lens that's made specifically for your particular astigmatism. So it's a funky shaped lens because it's going to have different focal points, just like your eyeball has different focal points. And we'll bring all those focal points in line at one point and correct the astigmatism. Okay, that's all for chapter 6, and then next chapter is the one right after 6, chapter 7.